Molecular translational energy. In scientific terms, heat is internal energy that flows from a system of relatively high temperature to one at a relatively low temperature. The internal energy itself, identified as thermal energy, is what people commonly mean when they say heat. A form of kinetic energy due to the movement of molecules, thermal energy is sometimes called molecular translational energy. Temperature is defined as a measure of the average molecular translational energy in a system, and the greater the temperature change for most materials, as we shall see, the greater the amount of thermal expansion. Thus, all these aspects of heat itself, as well as the thermal energy, temperature, and thermal expansion, are ultimately affected by the motion of molecules in relation to one another. Matter expands on heating and contracts on cooling. The expansion of matter on heating is called thermal expansion. There are some applications of thermal expansion in day-to-day life. Some of them are the following. First application is gap in railway tracks. Expansion joints of a different design can also be found in highways and on highways of rail. Thermal expansion is particularly serious problem where railroad tracks are concerned. Since the tracks on which the trains run are made of steel, steel, as noted earlier, expands by a factor of 12 parts in 1 million for every Celsius degree change in temperature. And while this may not seem like much, it can create a serious problem under conditions of high temperature. While laying railway tracks, a small gap is left between adjacent rails. This is because the iron rails expand in summer and the gap allows space for the expansion. Second application is cracking of glass. In this application, we need an empty glass jar and a boiling water. Glass has a very low coefficient of volume expansion, which is 0.2, and that of Pyrex glass is extremely low, which is only 0.09. For this reason, items made of Pyrex are ideally suited for cooking. Significantly higher is the coefficient of volume expansion for glycerin, an oily substance associated with soap, which expands proportionally to a factor of 5.1. Even higher is ethyl alcohol with a volume expansion coefficient of 7.5. When boiling water is poured into a thick glass, it cracks. This is also an effect of thermal expansion. Glass is a poor conductor of heat. It does not allow heat to pass through it easily. When boiling water is poured into a thick glass, the inner surface of the glass expands more rapidly than the outer surface. Due to this uneven expansion, the glass cracks. The third application is all about thermometers. In this experiment, we need a thermometer and the warm water. In a typical mercury thermometer, mercury is placed in a long, narrow, sealed tube called a capillary. Because it expands at a much faster rate than the glass capillary, mercury rises and falls with the temperature. A thermometer is calibrated by measuring the difference in height between mercury at the freezing point of water and mercury at the boiling point of water. The interval between these 2 points is then divided into equal increments in accordance with one of the well-known temperature scales. For the last application, freezing of water. In this application, we need ice tray and water. At 32.9 degrees Fahrenheit, water reaches its maximum density, meaning that its volume for a given unit of mass is at minimum. Below that temperature, it should continue to decrease in volume per unit of mass, but in fact, it steadily begins to expand. Thus, it is less dense with greater volume per unit of mass when it reaches the freezing point. It is for the reason that when pipes freeze in winter, they often burst, explaining why a radiator filled with water could be a serious problem in very cold weather. In addition, this unusual behavior with regard to the thermal expansion and contraction explains why ice floats in solid water is less dense than the liquid water below it. As a result, frozen water stays at the top of lake in winter. Since ice is a poor conductor of heat, energy cannot escape from the water below it in sufficient amounts to freeze the rest of the lake water. Thus, the water below the ice stays liquid, preserving plant and animal life. Try rubbing your finger against the edge of the wine glass. They'll make a sound, don't they? In fact, it is almost like a musical instrument when used and played by a musician. So, what are the materials needed for this experiment? Start by getting an empty wine glass, and then you wet its edge, and along with your finger, start rubbing it against the edge of the glass. This will take a lot of practice to make a sound. If water is applied, the mass of the glass increases and the volume of the air within the glass lessens. As this happens, the glass vibrates in a larger and farther apart waves, and the larger and more farther apart the waves are, the lower its tone becomes. An up-close look on the water shows the produced vibration following the finger as it cycles around the edge of the rim. Have you ever wondered how exactly is the sound produced? As you rub your finger against the edge, slipstick motion occurs. In this motion, the finger slips and sticks continuously on the rim of the glass, causing it to vibrate on its natural frequency. As it vibrates, the air around the glass vibrates as well, causing a sound to be produced. Acoustic resonance happens when the air molecules vibrate at the same frequency as glass. Changing the speed or pressure from the finger can make the sound softer or louder, but it does not change the frequency of the glass. This is Karl Javero signing off.